Hello and welcome to the introduction video of the MBR simulation for process design. Toray has simulation technology that customers can utilize to design your MBR process. Let's begin. This figure shows the different roles within a water treatment project. The membrane company makes the process designs for the engineering companies, and the engineering company makes the plant designs and constructs the plants. The process design includes the number of modules, operation conditions such as filtration flux and cleaning interval, and the replacement interval of modules. As an example of process design, having a lot of modules leads to an increase in initial cost. On the other hand, a few modules lead to increased running costs due to increased cleaning frequency. Total cost is determined based on initial cost and running costs such as chemical and power costs. Therefore, a highly reliable process design is required. The membrane company's process design is completed according to feed water category and sludge qualities based on previous operation data. The low reliability of new feed water was a problem without previous operation data. Another way to design processes is to create them using a pilot test. Pilot tests are a reliable method based on actual membrane operation in specific conditions. However, a pilot test must run for an extended period and can be expensive due to the size of pilot projects. So, we developed MBR simulation as a process design tool. The concepts are quick response, low cost, easy to use, and high reliability. This is the basic operation method of an MBR module. An MBR repeats filtration and relaxation. Physical cleaning by aeration recovers filtration resistance. However, filtration resistance gradually increases due to membrane fouling. When filtration resistance reaches the upper limit, CIP is conducted. CIP is high concentration chemical cleaning. In some cases, maintenance cleaning occurs to recover filtration resistance. Maintenance cleaning is low concentration and short-time chemical cleaning, compared with CIP. As you can see, physical cleaning by aeration and chemical cleaning are both conducted to recover filtration resistance. This is the fouling model of simulation. In this model, membrane fouling is classified three types: the reversible cake, the irreversible cake, and the pore clogging. First, the reversible cake is formed due to sludge accumulation on the membrane surface, which can be detached due to shear stress of aeration. Second, irreversible cake. After long time operation, a part of reversible cake is converted to irreversible cake. This cake is hardly detached due to shear stress of aeration. Third, pore clogging is preceded by foulant's intrusion into membrane pores. This is the image of filtration resistance of each fouling type increase with operation period. We built up basic equations based on this model. Fouling of the membrane is broken into three types: 1. Reversible cake, 2. Irreversible cake, and 3. Pore clogging. The fouling rate depends on the sludge characteristics that change with the raw water type and its condition. In these equations, sludge characteristics are considered. Alpha 1 is used to describe the pressure dependency coefficient of cake. Alpha 2 to resistance coefficient to the amount of cake. K tau 1 to inhibition coefficient of shearing. K tau 2 to friction coefficient of cake. Gamma to detachment coefficient of cake. And lambda to rate coefficient of pore clogging. We define these parameters as fouling parameters. The fouling parameters required for the simulation are acquired through the analysis of laboratory filtration test results. This is the schematic apparatus. In the tests, a small amount of the activated sludge from the MBR plant is repeatedly filtrated in varying conditions. For example, the fouling parameter, the pores clogging rate coefficient, is calculated by repeated filtration with sludge sample exchange. This is the simulation program flow chart. In this program, at first, we input simulation conditions. Input contents are sludge characteristics including fouling parameters, operation conditions, and module specifications. As the output, The TMP variation with operation period is estimated with considering the hydrodynamic pressure loss of inside MBR module. A TMP variation output is shown in this figure, which shows CIP interval. This slide is the verification of simulation result focusing on 3 fouling types. In this figure, the horizontal axis indicates operation period and the vertical axis indicates filtration resistance. These plots shows actual filtration resistance of each fouling type. And, these broken line shows simulation results. As you can see, the simulation results of all fouling types were very close to actual results. This is the comparison of the simulation result and the actual TMP. This graph's horizontal axis indicates the operation period, and the vertical axis indicates TMP. The brown plot shows the actual TMP and the blue line shows the simulation result. As you can see, the simulation result was very close to the results of MBR plants. This slide shows the verification of the TMP simulation. We verified our simulation technology with sewage and industrial wastewater cases. As you can see, good correlations were observed for sewage and industrial wastewater, confirming the reliability of the process designed by MBR simulation. With this, we have finished introduction of the MBR simulation. Thank you very much for your attention. If you have any questions, please don't hesitate to contact us.